Good evening. I'm Doug Crockford. I'm going to talk about JavaScript on the server side. 6 years ago, there was a big change in the way we thought about JavaScript when the Ajax revolution started. And we're now starting to see a similar change in the role of JavaScript going back to the server. But this is not a new idea. We first saw server-side JavaScript in 1996. Netscape had a product called Livewire. Unfortunately, it failed. It was a PHP-like implementation. It was a templating system with blocking I/O, very much like everything else. And that turns out not to be the best way to write servers. So now we're very excited about systems like Node.js, which is based on Google's V8 engine, which is bringing an event-driven, turn-based execution model to server-side implementations, and this looks like a big win. So Node.js allows you to implement a web server in a JavaScript event loop. Node.js is basically a high-powered event pump. It executes events very, very quickly. It does I/O correctly, in that every programming language since Fortran has done I/O blocking. And it turns out that's the wrong way to do it. You want to be non-blocking, and Node.js gets it right. So here we see we're calling the file system, asking to read a file. We pass it a callback method, or a callback function, which will be called with the result. We don't wait for the result. That turns out to be the right thing. Everything in Node.js is non-blocking, which is great. That's not quite true. There are some synchronous functions, and there's require. Neither of those block. I think that's a problem, but we can work around that. So one of the really nice things about working with Node.js and working with YUI is that because YUI 3 runs in Node.js, you can run exactly the same application on both ends of the network. You can be running on the server, or you can be running on the browser, same code. There are lots of reasons for why you'd want to do that. One might be that you've got an application which takes a long time to get started in the server or in the browser. So you can do the first page view in the server and send that to the browser so the user's got something to look at while the rest of the page is being assembled. Or you might be working with old-fashioned browsers like IE6, which cannot do the modern things. So in that case, you can run everything on the server side and simply send page views over. The thing that makes this possible is that it uses turn-based processing. Turn-based execution is a very polite way of scheduling work within a process, because everything waits for its turn, and when it gets its turn, it will not be interrupted until its turn is finished. The way this happens is we have callback functions which are called as a result of external events or user actions or the ticking of the clock. The nice thing about a turn-based system is that we don't need threads. So there are no races, there are no deadlocks, none of the hazards that come with threading. But it requires that you obey the law of turns. And the law of turns says that you never wait, you never block, and you finish fast. This is a different style of programming than we see in more old-fashioned systems. So in a turn-based system, nothing can ever block, not even I/O. So it means that you can't do polling. There are systems where you'll sit in a loop and you'll wait for something to happen. You cannot do that in a turn-based system. Instead, you register a callback, and so you get notified when the thing actually occurs. This is how browsers work. The browser has always worked this way. And it turns out this is how servers should work as well, and we're now coming back to that. Now, not everything can run well in a turn-based system. For example, if you have something that's going to be doing a lot of computation, it might be that it cannot finish fast, and so you have to do something else. But even within a turn-based system, you have two alternatives. One is a technique called iteration, where you can break the long-running task into multiple turns. Each turn, as it finishes, will schedule the execution of the next turn. And that will allow it to play politely, the system remains responsive, that one task may still take a long time, but none of its turns will take a lot of time, so it's okay. The other is to move the task into a separate process, like a worker. Google did some great work in promoting workers. So this is important because threads are evil. In systems programming, threads are a necessary evil. In application programming, threads are just evil. And so we don't want to be doing threads at the application level. It's too dangerous. Threads provide a deceptively simple model of concurrency, but it comes with a lot of complexity because threads are subject to races and deadlocks. So people for years have been wishing that we could have threads in JavaScript. And it turns out it's never going to happen, and it's a good thing that it's never going to happen. And let me show you why. So here I've got a program that's going to have 2 threads. Each of the threads is going to try to add a letter to an array. Now, because in thread systems you can't guarantee the order of execution, one result might be A and then B, or another result might be B and then A. This is a race, but this is not a problematic race. Another race that could occur in this program is we get an array containing just A, an array containing just B. And you might look at the code for hours and try to figure out what happened to the other letter. So the other letter was lost. It's a data error due to racing. So when you append something to the end of an array, what's really happening is something more complicated, where we're looking at the current length, we're looking at the new index. If the new index is greater than or equal to the length, then we add 1 to the length. Now, if we have 2 threads that are trying to do the same thing, we cannot guarantee what order these steps get interleaved. So one possible interpretation of this program is that both threads get the current length, and both will assign using that length, and then both will increment using the same length. And so that is how one of the letters can get lost. And again, this is a really, really difficult thing to debug. And fortunately, in the browser, we never have to deal with this kind of stuff. It's impossible to have application integrity when you're subject to race conditions. And races will occur anytime you've got threads that are competing in a read, modify, write cycle. One alternative is to never do read, modify, writes. And there's some systems that avoid having any side effects or any mutation. That turns out to be really difficult in applications, and so that's not a viable alternative. Turns work much better. So another thing we can do within threads is take advantage of mutual exclusion. At various times it's been called different things: semaphores, monitors, rendezvous, or synchronization, which prevents 2 pieces of code from executing at the same time. This used to be operating system stuff, but it has turned into application level stuff, partly because applications are now using networks, and networks impose very long delays. And also because of the multi-core problem, because we don't know how to make CPUs go faster anymore, we're making more CPUs and expecting the application developers to take advantage of that new capacity. And it turns out we don't know how to do that. That's an unsolved problem. The other problem you have when you do mutual exclusion is deadlock. So here we have 2 threads, Gaston and Alphonse. Each is programmed to wait for the other to stand up before he'll stand up. That'll never happen, so they are deadlocked. This is a real-world example of deadlock. This is an intersection in Sao Paulo, Brazil, about 2 blocks from the Yahoo office there. Each of these cars is a thread waiting for the car in front of it to resume before it can resume. Let's see, how am I doing on time? I think I'll skip this. Remote procedure call turns out to be a really bad idea, and ask me later why that is. So turn-based programs avoid all of these problems. It's unfamiliar to non-JavaScript programmers because it's a new model, but it's very familiar to JavaScript programmers because this is how we've always done it. And so moving to the server is actually going to be pretty comfortable. Someone asked earlier if there's going to be a test. and it's right now. Okay, so here I've got a function called funky, takes a parameter 0, which it sets to null. I set an array, or a variable x to an array, and I call funky passing x. What is the result now of x? Anybody think it's null? Anybody think it's an empty array? Okay, not a lot of hands going up. It turns out to be an empty array, because what funky gets is not the variable, it gets the contents of the variable. Here's another one. I'm going to swap two things, but this swap function actually doesn't accomplish anything because it doesn't see the names of the variables x and y. It only sees their values. So understanding that, we want to make a function that will put a value into a variable after some computation has been finished. So the worst way to do that would be to use eval to construct an assignment statement that's going to assign something to that. Not only is that really evil, it's going to be illegal in ES5 strict and in all versions of the language going forward. So you don't want to be doing that. And equally evil is assigning to a global variable indexed through the window object. We don't want to be doing that either. So an alternative to that would be that we pass not just the name of the variable, but also an object in which that variable is going to occur. So we change it from storing into a variable into storing into a property of an object. This is much better, but it's still not good in that it gives the doIt function too much capability. In addition to storing something into that property, it can do anything it wants to the rest of the object, and we don't want it to be able to do that. So the correct way to do that is to pass a function to doIt. And once doIt has the result, it can simply call that function. And the function is then responsible for taking care of it. This actually has some very nice security properties because doIt cannot abuse the function. It can't open the function up and get its private data. And the function cannot abuse doIt the way eval could. And in this model, that function that we passed is a callback. Callbacks are great. Callbacks provide temporal isolation so we can have events crossing different turn boundaries. We can use them for event handlers, for timers. They are lightweight, powerful, and expressive, and JavaScript does a brilliant job of enabling these things because its functions are so powerful. I've got my doIt function, and I call it pass it a callback, and then I call the callback when the thing is finished. And that works really well. And the thing that I pass it could be a function which will then assign something to a variable or assign something to a property in a variable. Now you might be thinking, well, that's too much work. I don't want to have to write a function every time I want to store the result of something. So I can generalize that. I can write a function which will return a function. So I only have to write that pattern once, and then I can call it as many times as I want to produce the functions that I want. So that makes it a little easier. And I can go meta on this stuff. Here I'm making stores that store to any object. I can make a store maker that will store things into a particular object. And once I make one of these stores, then I can call it to make functions which will make things for me. So we can make more and deeper functions in order to make life easier for us. Now, one way that doIt could still abuse us is it could call the callback more than once. So if we want to be able to restrict it, we can create a new function called once, and we will pass a callback function to it, and it will return a callback function which can only be called once. And we can then pass the result of once to doIt, and doIt can call it once, but no more than that. So now we're starting to be able to compose callbacks, where I can have functions which take callbacks, returning callbacks. I might have several things I want to have happen. So I can have a sequence function which will take a number of functions as arguments and return a single function which will do all of those things. And so that compose several results, which I could then pass to the doIt function. Another model might be I want to be able to revoke something. So instead of saying that it can call something once, I will determine when it can no longer call something. It can call it as many times as it wants prior to that and not after. And so in this case, I return two functions. One is the callback that can be revoked, and the other is the revoker function, which will cause the other callback to become inert. So this shows an example of creating a sequence of stores which can only be called once. So I can compose these things because functions can call functions and they all return in a nice nested way. I can build very complicated expressions simply by nesting the functions together. Now when we get to the server, we get some patterns in callbacks that we don't see in the browser. For example, in building a page, we might want to call 20 different web services and wait for all of the results to come back and then build the page and send it out. Doing it in PHP, you would have to call each of those things serially. Now, it's possible in PHP to call them in parallel, but that's work, and it's hard, and nobody wants to do hard in PHP, so you don't do that. So you just wait for each one. But in JavaScript, it all wants to be event-oriented, so it's easy. The complicated part is then synchronizing when all 20 of those things finish. That's a tricky bit of programming. The other problem is sometimes you'll have several services, each directly dependent on the next one. And so you don't want to have deeply nested event handlers because that turns out to be really crufty and difficult to maintain. So I want to solve these problems, and JavaScript gives me the power to do that. So I'm going to start by creating a new abstraction that I call a requester. So when I want to do something, I will create a function that will do it for me. And the function will take a sync function, which will be a callback that it will call. And it will then call some request service. You know, it might be XML HTTP request or IO or something like that, passing in a parameter, and also passing it a callback function. The callback function will receive the result and do something interesting with it and call the sync function. It will also take an error argument. The reason for that is that event handling exception handling doesn't work across turns because at the end of every turn the stack goes to 0. And what throw does is unwind the stack, so there's no way to throw something into a previous turn. But we've already got a callback function for the successful result, so we can also pass the error condition, and that takes care of the error result. Now you might be looking at this and going, well, this is too much work. It used to be I just call something, and now I have to write two functions in order to call something. And you go, yeah, you're right, so we should make that simpler. And so the answer to that is we'll write another function. And so what that function will do is we'll pass it our object of parameters, and it will return the function that calls the function that calls the function. So we don't have to do that stuff except once. And then from that point on, it's easy. We just call the request maker with the parameters, and we're all done. Now you might be asking, okay, so what's the benefit of that? Well, the benefit is we can now compose these things. So I can have a parallel function, and the parallel function can take an array of these requester functions, and it will then call all the requester functions immediately and get them all started, all 20 of them or however many there are. And when they all come back, it will then call your sync callback to let you know it's all done. And while it's doing that, it can also do some useful things for us like process timeouts. You know, so if any of those don't finish by a certain time, we can error out and not just leave it hanging. Or I could have a sequence function. And what the sequence function will do is take another array of requester functions, and it will call each one individually, passing it the result of the previous one. So it's sort of a reduce function. And so this becomes an easy solution to I want to call a bunch of things and have their results dependent on each other. Or another possible result would be to have a map function which will return an array of all of the results of all of the requesters. But I can go even further. I can now have functions which return functions which are those things, which gives me another level of composability. So I can have several sequences, and I can take all those sequences and then process all of those in parallel. So there are a number of other attempts at solving this problem which are also very elegant. There's a very nice paper out of the University of Maryland about arrows. Arrows are a very nice sort of monadic way of structuring stuff. There's the reactive extensions for JavaScript being developed at Microsoft, which is brilliant, where they're taking also an event-driven model, sort of reversing link and making it very nice. It's not adequately documented yet, so I don't know how to use it, but it looks to be brilliant. There's also Jed Schmidt's Fab, which is just amazing, where he's got these little functions which take functions and return functions, and he just cascades invocations. It's this amazingly twisted, weird, wonderful thing, also completely undocumented, so it's not viable yet. Ultimately, what I hope to do is to have a beauty contest in which we take these and other proposals and rank them and decide which is the most expressive and which is the most elegant, and we'll decide that, okay, that's how we should do server-side programming in JavaScript. I don't think we're quite ready to do that pageant yet, but I'm confident we're going to have some very lovely entries in it. I'm about out of time, so thank you and good night.